Welcome. Good morning. Did everybody get my email that we're going to have our labs at 2 p.m. this week? So both groups will meet at 2 p.m. today and then also again on Wednesday. What we're going to be doing is talking about the design of experiment activity. And you'll remember maybe from the syllabus on the fluids lab that 20% of your grade is based on an experiment that you design. And so you're going to get the instructions on how to do that today, and we'll go over an overview of the equipment so that you're familiar with the resources you have available as you design the experiment. All the details today and tomorrow at 2 p.m. Also the reminder that you've got back-to-back homework assignments this week. So homework 5A is due maybe 1 minute ago. Homework 5B is due Thursday at 11 o'clock. We'll talk about a couple of those problems today. I've got some key ideas and a couple of hints that I'll give you on those. In addition to review some of the ideas related to reservoirs and then a couple of applications of continuity equation. So any questions related to the announcements before we get into this new material? All right. One of the problems that you've got on your homework assignment is a little bit different from anything else we've done so far. Although you can apply most of the same principles. If you look at this, you'll see that we've got it's very obviously a control volume type problem where we're going to draw an imaginary boundary around this closed tank and keep track of what goes in and what goes out. And so if you look at the flows in, it's flowing in at A and B, and it's going out at C. So what makes this a little bit different is that it's a mixture of fluids. What's coming in at A is different than what's coming in at B. So in the past, you've been able to solve problems like this on a volumetric basis because it was just water going in and water going out. But in this case, you can't solve it on a volumetric basis, and instead you're going to have to solve this problem on a mass basis because mass is conserved always. Volume is conserved usually, as long as it's a single fluid, but in this case there's two different things, and so you have to be a little bit more careful. And so to find the outflow at C, what you're going to need to do is find the mass flow rate, average velocity, and specific gravity at C. And so the key idea here is that inside of the control volume, since it looks like this closed tank is full and there's no capacity for storage, there's not going to be any change of mass in the control volume over time. And so the mass flow rate in will be equal to the mass flow rate out. And density is defined as, for whatever this fluid is the specific gravity multiplied by the unit weight of water. So here you've got a specific gravity of 0.95 at A and 0.85 at B. So you can find, since this is already giving you the S and the volumetric flow rate, you can find the mass flow rates pretty easily, and that's the in. And now for the outflow rate, the mass flow rate out is going to simply be the sum of A and B. They've given you the volumetric flow rate, but not the mass flow rate. So I think that sort of heads you in the right direction on that problem. I hope, anyway. Just to refresh your memory, is maybe a long weekend, and it's easy to stop thinking about the continuity equation over the weekend, although you had plenty of homework to keep you busy. Let's just take a review look at a reservoir type problem like this. So this is similar to the in-class exercise homework, remember, where we were looking at how long it would take to drain a certain reservoir. So at this point, though, what we want to know is there's a certain volume coming in, a certain volume of discharge through a dam going out. And so at this given instant of time where we've got this flow rate in and out, then we also know the area of the reservoir. And anybody know what a hectare is? Here it's explained in terms of hectares. Do you know how many square feet there is in an acre? 43,560 square feet in an acre. So that's pretty random and bizarre, right? So the SI units of area, a hectare, is 100 meters by 100 meters. So it's a lot more straightforward than that. So you may want to write that down in your margins there. We're saying the surface area of this reservoir at this instant of time is 10,360 hectares. So that means 10,360 times 100 times 100 if you wanted the surface area in terms of square meters. So you're going to need that in order to find the rate of the rise of water. So how quickly is the water level going up in terms of meters per hour? So you've got some units conversion there, some time conversion, and then also applying the continuity relationship. Remember that the accumulation is the difference between in and out. So 0.148 meters per hour is how quickly that should be rising at this point. But remember that the cross-sectional area could be changing the deeper it gets. And usually what happens is that as a system becomes flooded, it spreads out the water over an even larger area. So that even if the in and the out stayed the same, we could expect that that rate of rise would decrease as the amount of land area that is flooded goes up. So with the cross-sectional area. So we know that what I'm calling here the V rise, you know, the velocity that the water is rising, even if the Q rise stays the same, the area could change. And so as the cross-sectional area that gets flooded increases, then the velocity that it's rising goes down. And that's commonly seen in situations like where the Mississippi River is flooding, or you know, when the Ohio River is flooding, that the higher it gets, the speed that the water level rises decreases. So any questions related to this application of the continuity relationship? You can solve it on a mass basis, of course, but in this particular case, since there's no mixing, you can do it on a volumetric basis, maybe even a little bit easier. 0.148 meters per hour. Okay. Now, we've talked about the orifice equation in the lab. The idea that, you know, there's an interchange between potential energy and velocity. And so I don't think we've ever derived the orifice equation, but if we consider two different points, what we can say is that at location 1, which is at the top of the tank and open to the atmosphere, if we were going to have the pressure head, the elevation head, and the velocity head, and then consider the same things at 2, P2 divided by gamma plus Z2 plus V2 squared divided by 2G. So at the surface of the reservoir, there's not going to be any pressure because it's in contact with the air, and so we'd cancel out the pressure head term, and there would be no velocity at 1. Now, we're assuming maybe there is a little bit of velocity if the water level on the tank is going down, but it's going to be so small relative to the other terms of the energy equation that we could neglect that. And I mean, unless it's a very narrow pipe, the velocity that it's decreasing really will be pretty small. So it's not necessarily 0, but it's negligible. So we'd cancel out the velocity head term at 1. So all we've got at location 1 is some energy above a datum, and so Z1. And in this drawing here where we're calling it H, we're saying that H is the difference between Z1 and Z2. So H is just Z1 minus Z2. So I cancel out the Z2 term from the right-hand side of Bernoulli's equation. And an important thing to note about a jet of water, and this is going to be particularly important for one of your homework problems that you've got, the last homework problem that's due on Thursday. When water comes out of an orifice, even though it had pressure inside the tank before it came out of the orifice, as soon as the water goes out of that orifice, it immediately loses all of its pressure. And so that's a big loss of energy, a sudden large decrease in energy. But some of that pressure was translated into accelerating the water through the orifice. The main thing we're going to do is cancel out this pressure head term so that H, which is the difference in elevation, is just equal to V2 squared divided by 2g. And so if we want to solve for the velocity, that's where square root of 2gh comes from. It's just Bernoulli's equation applied between those 2 points, at the surface of the reservoir and just after the opening of the jet. Now, let's combine the orifice equation with the idea of the Reynolds transport theorem, which is where we are keeping track of the movement of fluid through control surfaces and either the accumulation or the loss of mass inside of a control volume. So here's when we rearrange the Reynolds transport theorem in terms of mass flow rate, and we say, well, the mass of the system isn't changing over time, but there can be a change in mass inside the control volume. So here we're saying that the flow rate out, if location 1, here we've, I guess, started calling this orifice location 1 in this sketch, V1 times A1 is going to be the volumetric flow rate out. And the area of the tank, if this is a circular tank, and the liquid level is decreasing at the rate of dH dt, so that's how quickly the water level is going down, then that's similar to in the previous example we were working on where I was calling it a Q rise. It's just the accumulation expressed in terms of a volume. So here, the storage loss is a negative value because the water level is going down over time as it flows out through that orifice. Since it's flowing out of the orifice, the water level is decreasing, and so the area of the tank multiplied by the velocity that the water level is going down. And so in other words, the loss of accumulation is equal to the flow out. So what we can do is substitute in the orifice equation here for 1. That velocity out is based on the orifice equation, which of course is in terms of h. And so in the next sequence of equations here, what we do is we say substitute in the orifice equation for the velocity. And so we've got the velocity out multiplied by the cross-sectional area out in that opening. And so the volume out per time is equal to the loss of volume in the control volume, the loss of fluid inside the control volume. And then just rearranging to isolate the t on the left side and terms of h on the right, and then you integrate. So what this ends up telling us is over time how long it takes for the liquid level to fall from some initial height to a certain height h that you specify. And so we can find out for a certain cross-sectional area of a tank and a certain opening area at the orifice the duration of time it takes to fall between 2 heights. Now it's important to point out that this isn't the h values here aren't the distance that it's fallen down, but rather it's the beginning height above the center of the orifice and then the height above the center of orifice at time t. So there's a difference between the height of the water and how far it's fallen. And you'll understand that distinction here in this example, where we have a circular tank, and the tank itself has a diameter of 500 millimeters, but then this orifice where the water's flowing out only has a diameter of 15 centimeters. So initially, the height of the water at a certain time was 2.5 meters, and we want to find out two steps here. In the first step, how long will it take to fall a distance of 1.1 meters? And remember, this the h naught is the initial height, and then h is the height of the water above the orifice. And so you're going to have to do just a little bit of math at the beginning. Don't directly substitute the 1.1 in as h. But in part B, we want to find out, take a look at the nonlinearity that, as the liquid level decreases, so does the outflow. And we want to just sort of prove to ourselves that this equation is going to take that into account, that as the water level is getting lower, then the flow rate out is decreasing. Because I think what this equation is going to show you is that the first 1.1 meters that it falls, it's less time than how long it takes for it to fall the next 1.1 meters, because the velocity out is going to be decreasing over that duration. All right, so let me pause the recording, allow you to apply this equation twice, once in part A, once in part B, and we'll find out what those times are. Okay, so we've got this tank of water, and it's coming out of an orifice, and we want to find out how long is it going to take to fall a distance of 1.1 meters if it's initially at 2.5 meters. And we have to do some preliminary calculations here, find the area of the orifice, find the area of the tank. We're given that formula to solve for the time. So that first 1.1 meters, it's going to take 2 seconds for it to drain that much. And then, rationally, just thinking about what's happening here, since the water level is getting lower, then you actually saw this in the lab, that as the water level goes up, the stream is going faster and it flattens out. And then as the water level in that piece of equipment got lower, then the stream wasn't shooting out as far. And so it should take longer, right? So that's what we kind of know in the back of our heads as a reasonableness check. And if we actually substitute in the values, then it looks like it should take 3.19 seconds for that second 1.1 meters, the additional. So what that means is that it's starting at the 1.4 from above, and it's falling another 1.1 meters, which means that the final height of the water above the center of the orifice will just be 0.3 meters. Now, one thing to point out is that that area of the opening, that's not in the square root. And it's easy, sometimes it's a mistake that's easy to make, is see how the square root of 2g is down there in the denominator, but the area is not inside of that square root of 2g. So that's an easy calculation mistake to make. Any questions about this example? All right. Okay, we've worked with nozzles before, and as I said before, Chapter 5 is an easy big idea, continuity relationship, but sometimes when we combine it with other ideas from earlier in the semester, that's when things get a little bit complicated. So in this example, what we're doing is we're combining the hydrostatic equation, which is what we apply through a manometer. This differential manometer is able to measure the difference in piezometric pressure between 2 points. And so here we've got air that's flowing through a nozzle. And let's just assume that as the air is flowing through the nozzle that the density is constant. Maybe that's a good assumption, maybe it's not. Remember, Bernoulli's equation says that it's an incompressible fluid. So we'll just take that at face value here for a moment and say, here's our incompressible fluid that is inviscid. We're applying Bernoulli's equation along a streamline for steady flow. And we want to find out what's the deflection in the manometer. If we know that the area at 1, so here where it's wide, the area is double where the area at 2 is narrow. So here this first bullet point is saying A1 is double A2. So then that means we know the velocity at 1 is 30.48, so the velocity at 2 is going to be double that. Okay, so continuity relationship is what tells us the relationship between the two velocities. And we can apply that to Bernoulli's equation to find out how the pressure is changing, and then apply that to the hydrostatic equation inside of that manometer to find out the deflection in the manometer. And you may remember from a previous example we worked that when we were working with a differential manometer like this, it was when we were doing the pitot tube, we had a similar kind of a situation, and what we figured out was that the change in piezometric pressure is what this differential manometer is actually measuring, and that is the height of the deflection multiplied by the difference in the unit weights between the manometer liquid and whatever else there is. And in this case, it's air. So you'll notice that I've given you the air density, and if we know the air density, we can find the unit weight of the air just by multiplying this density by g. Just remember, gamma is density times g. So here we want to solve for the delta H. It's going to be maybe a three-step process to do that, where we first start off by finding the velocity with the continuity relationship, and then in the Bernoulli relationship we're going to find the delta PZ. And remember, what we mean by PZ, P sub z is P plus gamma z. So PZ1 is P1 plus gamma Z1. PZ2 is P2 plus gamma Z2. So we can rearrange this Bernoulli's equation so that on the left-hand side of Bernoulli's equation is delta PZ, and on the right-hand side of Bernoulli's equation is the other factors that will allow us to find a value for that to then substitute it into this differential manometer equation, which is essentially the hydrostatic equation. All right, so I'm going to turn you loose on this one. It's, I guess, a three-point application of the continuity relationship. Okay, we take care of the preliminary stuff at the beginning, you know, like finding the V2, calculating the unit weight of the air based on the given density of the air. And I know these examples, when you're just doing it in the margins of your notes in class, you can't afford to write out all the units maybe because you don't have the space, but I'd really encourage you to make a habit on the homework and on the exams to try and be as clear, detailed, and like really specify what things are. If something's a velocity, give it units of meters per second. If it's a unit weight, make sure it has units of newtons per meter cubed and so on, because keeping consistent with that can really help you to avoid mistakes, or if you've made a mistake, help you to identify it and correct it. So doing this preliminary stuff, we get the velocity at location 2 is double what the velocity at 1 was. So 60.96 meters per second. And then rearranging Bernoulli's equation in terms of P sub z puts delta PZ on the left is equal to density divided by 2 multiplied by the difference of the velocity squared. So the change in piezometric pressure is 1435 newtons per meter squared. And then that's what we then substitute into this manometer equation, which is just the hydrostatic equation, really. And so the change in piezometric pressure is equal to the deflection multiplied by the difference in the unit weights. And so in the end, you should get a deflection of 0.0914 meters. So that's what the deflection would be if we were working with this manometer liquid, which has a unit weight of 15,710 newtons per meter cubed. Who knows what that is? It's not mercury, but it's heavier than water, so some hypothetical fluid that has that property. Any questions on how to deal with this nozzle example? My sketch was a little sloppy here. I didn't show it as open to that nozzle, but it was open. It was measuring the difference in the pressure there. Okay, let's talk about an application of continuity relationship, and it's related to vapor pressure. We know that you can boil water by heating it up. We already know that, right? Another way to boil water is to lower the pressure that surrounds it. So when we heat water, what's happening is you're increasing the vapor pressure. So by heating up the water, you're increasing the kinetic energy of the molecules, and when it reaches 100 degrees Celsius, then the pressure, the kinetic energy of those molecules can be expressed in terms of the pressure that they exert against the atmosphere above it. And the pressure that they exert is equal to the atmospheric pressure at 100 degrees Celsius. And that's kind of why 100 degrees Celsius was defined as 100, is that's when water boils. That's why they picked that to be 100 on the SI scale of temperature. But the point is that you can see here this is a figure of the pressure as a function of temperature, the vapor pressure of water, here in terms of millimeters of mercury, here in terms of pascals. But we can get the water to boil at lower temperatures than 100 if we surround the water by pressures that are less than the vapor pressure of that liquid. And I guess the important thing to identify is what this word boil means. Boil is just talking about a liquid going into the vapor phase. And we usually associate boiling water with hot water, but it's not necessarily that it's hot. It's just that it's going into the vapor phase. And so did we already, I can't remember which class I've done things with. We already watched a video where they were pumping the air out of a vacuum and it was making the water boil that way, right? All right, I see some nodding heads, so you remember the YouTube video, good. Okay, so one implication of that is that let's consider water in a tank. So here's a tank on the left-hand side. Water is going inside of a pipe. Now this dashed line represents the piezometric head at a certain flow rate. So let's assume that there's no energy loss due to pipe friction. So that's why this line is horizontal, is we're just saying for now let's set aside energy losses. There's going to be a small decrease in the piezometric head through this throat. So why is the piezometric head going down through the throat? Remember what happens in there? Velocity goes up, pressure goes down. And so the piezometric head that we're graphing is just the pressure head plus the elevation. That's this piezometric head that's being graphed. We know that the total head, so this is the piezometric head, in your lab when you did a graph of the hydraulic grade line, what you were graphing was the piezometric head. The total head includes the piezometric and also the velocity head. Okay, so here where we've assumed that there's no energy loss, the total headline would be horizontal for all of it. But these different dashed lines are just sort of representing that there is an increasingly large dip at this contracted throat section as you increase the flow rate. Because as you increase the flow rate, then that velocity, where at the section where the diameter is really narrow, gets bigger and bigger. And remember that velocity is going to be Q divided by area. And area is pi d squared divided by 4. So if you make the diameter small, then the area is going to be really small. And so that as the velocity, the velocity is going to be getting higher and higher through this throat, and so that's going to mean that the pressure gets lower and lower. So you can get to a point where the pressure is actually below 0 when we're measuring pressure relative to gauge. And so all of these have been saying, you know, we're going to be measuring our pressures relative to the atmospheric pressure, but if the water's moving fast enough through this section, then what it means is that the pressure of the water inside that throat is actually less than the pressure of the air that's surrounding that pipe. So that if we like poked a hole in the pipe, instead of the water rising to a certain elevation, if we poked a hole there, it would actually start sucking air into the pipe. That's what it means that there's a negative pressure. So at the pipe that's immediately to the left, where we haven't contracted yet, if we poke the hole there, the water level is going to rise to a certain elevation. That's what the piezometer is when we've poked a hole and the tube is, the water's rising to a certain level. But in that section where the velocity is really fast and the pressure is low, then there's a suction. The risk is when the pressure goes below the vapor pressure of the water. These vapor pressures are absolute, measured relative to the vacuum of space. These aren't gauge pressures, but these are absolute. So what happens is when the pressure is really low inside of a pipe, then the liquid starts going to the vapor phase. It starts to boil, in other words. It's not hot, it's just that because the liquid itself has a really low pressure, then the water can start to go into the vapor phase, and these tiny little vapor pockets that form will only exist for just a little while. Because what you'll notice is that the pressure is low for a moment, but then as this pipe starts to expand again, the pressure is increasing, and so those tiny little vapor pockets will very quickly be forced to collapse. And it sends a shock wave through the water, and actually it can be quite damaging to the pipe. It can cause pitting in the pipe. Cavitation is not uncommon in ships or in boats. The propeller that actually moves the ship through the water. There can be a low pressure section on the backside of an impeller. It can happen in pumps a lot. We have to be careful in hydraulic design of pumps because negative pressures can occur. And so the main idea that you need to keep in mind is that the risk factor is when the liquid pressure falls below the vapor pressure of the fluid. If the liquid pressure is less than the vapor pressure, then cavitation can occur. And cavitation are these little air bubbles that are, they're not air bubbles, they're liquid vapor bubbles that will collapse and send a shock wave through the system. So let's diagnose, let's try and find out. For this system, what we have flowing through the pipe is water at 60 degrees Celsius. Okay? So the vapor pressure of water at that temperature is 20,000 pascals. And we also want to know the unit weight of water at that temperature. We're not going to use the typical unit weight because this is pretty warm water. So it's expanded slightly such that its unit weight is a little bit lower than we normally would utilize. So in this continuity example, first of all, we've already been given the velocities. So you don't have to solve them, but you do need to apply Bernoulli's equation to find out what is the pressure of the liquid at 2. And you'll notice here that the pressure that's given at 1, this 814 kPa, that's the absolute pressure. So if we wanted to know what was the gauge pressure, then we'd just have this 814 and we'd subtract 101.325 because that's the typical atmospheric pressure. But here, this is saying we've got P1 in terms of absolute, so let's find out what is P2 in absolute and then compare it to the vapor pressure to find out, is it higher, which means there's no cavitation, or is it lower, which means there will be cavitation. I think it's interesting to look at where is the energy at different spots. So at point 1, you'll notice that there's 84 meters of head existing as pressure and 20 meters of head existing as velocity. So the majority of the energy exists in the pressure head term rather than in the velocity head term at location 1. That's where the velocity was moving relatively slow, 20 meters per second. That's still super fast. Compared to typical flows through pipes. At location 2, there's 103 meters of energy in the velocity head term. So it's really, water moving that fast ties up a lot of energy in the velocity head, which means that it's going to bring the pressure way down. When we solve for the pressure at that location, at location 2, there's only 15,000 pascals there. And since that's less than the 20,000 pascal vapor pressure, then that means the pipe is going to have cavitation. So the question is it going to be dangerous cavitation? And that's a lot more challenging to know because it's going to depend on how abrupt the transition is from a high velocity to a low velocity. You know, if that transition is relatively gradual, then those cavitation bubbles would collapse more slowly. It depends on the strength of the pipe and its thickness, and so there are a variety of factors that can influence whether it'll be destructive cavitation, but the question, will the system experience cavitation? The answer to that is yes. So here is a picture of what happens to a pump impeller during cavitation. You can see that the impeller vanes are pitted, and there's been some damage there because if you think about a pump that's sucking water from some reservoir, here this triangle and the ripples are indicating a free surface of water. Try to make it as awkward as possible and discourage people. All right. Stick around to the end. All right. So here we've got a free surface of water, and that's where the pressure is 0. So the pressure is 0 here. It also means that the pressure is 0 inside of that pipe. So if the water is going to be moving towards the pump, then that means we're starting at 0 gauge pressure, and now the pressure is getting negative, more negative, getting closer and closer to the vapor pressure of the liquid. So in a pump situation like this, some of the things you can do to reduce the probability of cavitation is you don't want to have the pump too high above the water surface because that's something that can get you closer and closer to the vapor pressure, or if the suction side of this, if the suction side of the line is long, that's another thing that can tend towards cavitation. We'll talk more about that in hydraulics, the different ways that they measure the risk of cavitation, but you can see some of the effects. And this isn't just hypothetical, it happens in the real world as well. Back in the spring of 1983, they had a really wet spring in the watershed that feeds Lake Powell, which is in southern Utah on the border of northern Arizona. And so it was a really heavy winter, and then the spring came so quickly that there was a lot of snow melt at the same time that it was raining. So the reservoir was filling up quickly, so they had to send a lot of water through the overflow spillway, and there was some cavitation damage to the spillway. So we looked at the Oahe Dam and guys crawling down into the hole. Now you're looking at the Glen Canyon Dam and guys crawling down into the hole to try and investigate the extent of the damage there. And what they found out was actually that this was largely caused by cavitation, that the water was moving so quickly through the pipe that the cavitation that occurred sent little shock waves through the concrete lining and pitted it, and they were sending so much flow through the spillway. The velocity was high, the pressure was low, cavitation occurred, and the collapsing air bubbles, the collapsing vapor pressure bubbles was enough to scour the concrete, and it was a pretty expensive and time-consuming thing to get that spillway repaired before the next spring. Okay, well, in the 3 minutes that we've got left, let's talk about a couple of the homework problems. In this one, you've got a rocket motor, and you need to apply the idea of mass balance to this one. They want to know what's the velocity of the gas that's exiting the rocket motor. And I don't think they provide a picture, or if they do, I didn't like it, because I made my own little diagram here. So it's a solid booster that is burning at 1.5 centimeters per second. So that means that if you draw a control volume around this thing, then there is a decrease in the mass inside of the control volume. So here, the change in mass in the control volume over time is going to be negative. You're given the density of the propellant, and since we have the diameter of this circular engine, you can make an area out of that, and since you know the rate that it's being lost, you could, on a volumetric basis, find out the decrease in the propellant and then multiply it by the density to find the mass of propellant that's being lost over time. So the mass that's being lost there is the same as the mass that's flowing out of the motor, and you can use the gas law to find out the velocity of that. Now, of course, the density of the gas you can find by the pressure divided by RT, and the temperature is given. Here's an R value for that gas, and so you can find the density of the gas, and we know that mass flow rate is density, area, and velocity. So the area you can get from the fact that it's an 8 centimeter diameter there at the exit. And so in the end, they want to know the velocity of the gas exiting out of the rocket motor. The idea here is just that the mass of the solid is turning into the mass of the gases that come out through that control surface. So that's a little hint for problem 87. Now for problem 102, this one's tricky. And it all depends on you knowing that when the water comes out of a nozzle, that the jet no longer has any pressure. That if we apply Bernoulli's equation between the water in that jet and the water inside of this, it's like a syringe. Think of this as a big syringe, like a hypodermic needle kind of a thing, except for the water's just shooting out. They want to know, number one, what's the velocity of the water that's coming out? And that's actually a really easy part because they tell you the two diameters and the fact that the piston is going 6 feet per second. And so finding the velocity of discharge is kind of a negligible part of it. You're just applying continuity relationship to find how fast the water is moving that's going out. But then the trickier thing is applying Bernoulli's equation to find out, first of all, the pressure inside of this object. And then once you find the pressure, you're going to apply pressure times area to find the force. Because that's what they ask is, how hard do you have to push on this to get the water out at a rate of 6 feet per second for the piston and whatever that jet ends up being. So applying Bernoulli's equation, at location 2, you're going to know the velocity because you found it through the continuity relationship earlier. You'll find V2. Z1 and Z2 are equal since this is horizontally oriented. Z1 equals Z2. But the tricky thing that you got to remember is that for a jet, there's no pressure. And so P2 is equal to 0. So the only unknown in Bernoulli's equation is going to be P1. And once you find the pressure inside of that nozzle, then you can find out the force by pressure times area. And of course, they've given you the diameter, so you can find the area. Those are my hints. You've got your work cut out for you. It's due Thursday. I'll see you at 2 o'clock today or tomorrow. Have a good day.